2 Voltage imperfections in power systems. Topic 1 Voltage sags and interruption. Voltage sag is a short duration, from 0.5 cycle to 1 minute, decrease in RMS voltage magnitude usually caused by a fault somewhere on the power system. Voltage sag are usually associated with system fault but can also be caused by energization of heavy loads or starting of large motors. Interruptions a large decrease in RMS voltage to less than a small percentile of the nominal voltage or a complete loss of voltage. Interruptions can be the result of power system faults, equipment failures, and constant malfunctions. The interruption are measured by their decoration since the voltage magnitude is always less than 10% of nominal. Topic 2 Sources of sags and interruptions. Voltage sags and interruptions are generally caused by faults on the utility system. Fault on same feeder. The customer will expensive a voltage sag during the fault follows by are interrupted where the circuit breaker opens to clear the fault. Losing operating is successful. Interruption will be temporary. It will take 5 to 6 cycles to breaker to operate. Parallel feeder the customer will experience a voltage sag during the period that the fault is actually on the system. As soon as breaker open to clear the fault, normal voltage will be restored at the customer. 1. AC electrical loads are referred to whether as linear or no linear depending on that they draw current from the mains power supply waveform. 2. A load is considered non-linear if its impedance changes until with the applied voltage. 3. The changing impedance means that the current drawn by the non-linear load will not be sinusoidal even when it's connected to a sinusoidal voltage. 4. These non-sinusoidal currents contain harmonic currents that interact with the impedance of the power distribution system to create voltage distortion that can affect both the distribution system equipment and the loads connected to it. 5. This is due primarily to new power conversion technologies such as switch mode power supply, SMPS, which can be formed is virtually every power electronic device. 6. The SMPS is an excellent power supply, but it is also a highly nonlinear load. Here is the diagram of nonlinear load. Topic 4 IEEE and IEC Standards. IEEE Standards. 1. IEEE Power Quality Standards, Institute of Electrical and Electronics Engineer. 2. IEEE Power Quality Standards, International Electro-Technical Commission. 3. IEEE Power Quality Standards, Semiconductor Equipment and Material International. 4. IEEE Power Quality Standards, the International Union for Electricity Applications. 5. IEEE STD 5191992, IEEE Recommended Practices and Requirements for Harmonic Control in Electric Power Systems. 6. IEEE STD 1159-1995, IEEE Recommended Practices for Monitoring Electrical Power. 7. IEEE STD 1411993, IEEE Recommended Practice for Electric Power Distribution for Industrial Plants. 8. IEEE STD 1159-1995, IEEE Recommended Practice for Monitoring Electrical Power Quality. IEC Standards. 1. Definitions and Methodology 61000-1X. 2. Environment 61000-2X. 3. Limits 61000-3X. 4. Tests and Measurements 61000-4X. 5. Installation and Mitigation 61000-5X. 6. Generic Immunity and Emissions 61000-6X. Topic 5 Sources of transient overvoltages. There are two main sources of transient overvoltages on utility systems are I. Capacitor switching. 2. Lightning. These are also sources of transient overvoltages as well as many of other switching phenomena within end-user facilities. Some power electronic devices generate significant transients when they switch. Transient overvoltages can be generated at high frequency, load switching and lightning, medium frequency, capacitor energizing, or low frequency. Capacitor switching. 1. Electrical utilities switch capacitor banks during peak load hours to offset the lagging reactive power, kVAR, demand of the load, reducing the net apparent power, kVA, load on the circuit. 2. Switching of capacitor banks is accompanied by a surge of current, initially limited by the system's impedance and line resistance, followed by a voltage drop and then a voltage rise that decays oscillatory at a frequency determined by the circuit's inductance and capacitance. 3. Capacitor switching results in oscillatory transients, with the voltage rise typically reaching 1.5 to 2 times the nominal voltage. 4. Capacitors can be energized all the time, fixed bank, or switched according to load levels, with controls based on factors like time, temperature, voltage, current, and reactive power. 5. On distribution feeders with industrial loads, capacitors are often switched by time clock-in anticipation of increased load during the working day. 6. Common problems associated with utility capacitor switching overvoltages include trips and malfunctions of adjustable speed drives and other electronically controlled load equipment, often occurring at nearly the same time each day. Lightning. 1. Lightning can strike power lines directly, either on the primary or secondary side of the transformer, generating very high overvoltages. 2. Lightning currents can also flow along ground conductor paths, entering the grounding system through primary ground, secondary ground, or the structure of load facilities. 3. Even if lightning does not strike a conductor directly, it can induce impulses by the collapse of the electric field or by striking the ground near a facility, causing ground. Reference to rise. 4. Lightning surges can travel long distances along utility lines, causing multiple flashovers at pole and tower structures. 5. Surge arresters on the service transformer can intercept impulses from the phase wire, but may not survive multiple strokes of lightning. 6. Researchers suggest that lightning surges can enter loads through the interwinding capacitance of the service transformer, allowing high-frequency surges to bypass the turns ratio of the windings. Topic 6 Principles of overvoltage protection. The fundamental principles of overvoltage protection of load equipments are as follows. 1. Limit the voltage across sensitive insulation. 2. Divert the surge current away from the load. 3. Block the surge current from entering the load. 4. Bond grounds together at the equipment. 5. Reduce or prevent surge current from flowing between grounds. 6. Create a low-pass filter using limiting and blocking principles. Topic 7 Devices for overvoltage protection. 1. Surge arrestor and transient voltage surge suppressors. 2. Isolation transformers. 3. Low-pass filters. 4. Low-impedance power conditioners. 5. Utility surge arrestor. Surge arrestor and transient voltage surge suppressors, TVSS. 1. Asserters and TVSS devices protect equipment from transient overvoltages for limiting the maximum voltage. 2. TVSS are generally associated with devices used at the load equipment. 3. The elements that make up these devices can be classified by two different modes of operation, crowbar and clamping. 4. Crowbar devices are normally open devices that conduct current during overvoltage transients. 5. Clamping devices for AC circuits are commonly non-linear resistors that conduct very low amounts of current until an overvoltage occurs. Isolation transformer. 1. Isolation transformer used to alternate high-frequency noise and transients as they attempt to pass from one side to other. 2. The chief characteristics of isolation transformer for electrically isolating the load from the system transients is their leakage inductance. 3. Voltage notching due to power electronic switching is one example of a problem that can be limited to the load side by an isolation transformer. Low-pass filter. Low-pass filters are designed to pass signals with frequencies below a certain cutoff frequency while attenuating signals with frequencies higher than the cutoff frequency. They are composed of series inductors and parallel capacitors in general electric circuits, providing a low impedance path to ground for selected resonant frequencies. For surge protection applications, low-pass filters employ a CLC, capacitor-inductor-capacitor, combination to achieve better protection even for high-frequency transients. Voltage clamping devices like metal oxide varistors, MOVs, are added in parallel to the capacitors in these filters. Low-pass filters have many applications, including 1. Audio circuits for filtering out high frequencies. 2. Anti-aliasing filters for conditioning signals before analog-to-digital conversion. 3. Digital filters for smoothing data sets. 4. Acoustic barriers for attenuating high-frequency noise. 5. Image blurring by filtering out high spatial frequencies. The moving average operation used in finance is a particular type of low-pass filter, which can be analyzed using the same signal processing techniques as other low-pass filters. Low-impedance power conditioners. 1. Low-impedance power conditioners, LIPC, are used primarily to interface with the switch mode power supply, SMPS, found in electronic equipment. 2. The filter is on the output side and protects against high-frequency, source side, common mode, and normal mode disturbances. Surge arrestor. 1. A surge arrestor is a protective device for limiting surge voltages on equipment by discharging or bypassing surge current. 2. Surge arrestor allows only minimal flow of the 50 Hz per 60 Hz power current to ground. 3. After the high-frequency lightning surge current has been discharged. 4. A surge arrestor correctly applied will be capable of repeating its protective function until another surge voltage must be discharged. Topic 8. Utility capacitor switching. 1. This is one of the most common switching events on utility systems. 2. It is one of the main causes of oscillatory transients. 3. This transient can propagate into the utility's local power system, pass through its distribution transformer, and enter into the end user's load facilities. 4. A common symptom that directly relates to utility capacitor switching over voltages is that the resulting oscillatory transients appear at nearly identical times each day. 5. This is because electric utilities, in anticipation of an increase in load, frequently switch their capacitors by time clock. Here are the important questions from Unit 2. I will create a EPQ playlist and I will upload all units in Unit. It will be there in our channel. Please go and check it once. I hope you understood the video. If any queries you can ask me in the comment section. Please like the video, share it with your friends and don't forget to subscribe our channel.